Dear students, welcome back to the lecture series on solid state. In this session, we will have a detailed discussion on X-ray diffraction by crystals. We will see how crystals are used as diffraction gratings for X-rays, and this use of crystals as diffraction gratings for X-rays depend upon a famous equation or law called Bragg's equation or Bragg's law. So, in this session we will also see how to derive Bragg's equation and what is its significance. Before moving on to today's session, let's discuss the answers for the assignment questions of the previous class. The first question: what is the percentage of free space in a body centered cubic unit cell? We have four options: option A 30%, option B 32%, option C 34% and option D 28%. In the last class, we have seen the packing efficiency in various cubic lattices, namely face centered, body centered and simple cubic. And we have seen that in a body centered lattice, that is in a BCC lattice, the packing efficiency corresponds to 68%. Now, what is packing efficiency? It is the volume occupied by the spheres in the unit cell divided by the total volume into 100. And in a BCC structure, the packing efficiency is 68%. So, what will be the percentage of free space available? So, percentage of free space available will be 100 minus 68. So, that will be equal to 32%. So, here the question is asked about the percentage of free space in a body centered cubic unit cell. So, the correct option is option B, 32%. Second question: the most efficient packing is present in? We have four options: option A HCP and BCC, option B HCP and CCP, option C BCC and CCP and option D BCC and simple cubic cell. When we discussed about the packing efficiencies, we have seen that in a simple cubic arrangement, the packing efficiency was only 52.4%, whereas in a body centered arrangement BCC, it was about 68%. In a cubic close packing, that is CCP or FCC, face centered, it was the highest, that is 74%. Along with CCP, we have another close type packing called HCP, that is hexagonal close packing. The packing efficiency of hexagonal close packing is also equal to 74%. Okay. So, among these we can see that hexagonal close packing as well as cubic close packing has the highest packing efficiency of 74%. So, among these options, the correct option will be option B, HCP and CCP, where HCP is the hexagonal close packing and CCP is the cubic close packing. Both are equally efficient, having a packing fraction of 74%. Now, we will move on to the third question. The packing efficiency of the face centered cubic unit cell is, assuming that the atoms are touching each other. We have already discussed about the packing efficiencies in various structures, and we have seen that in an FCC or a CCP, the packing efficiency corresponds to 74%. So, Among these options, we have option A 68.04%, option B is 52.4%. So, option B corresponds to simple cubic. Now, we have option C. Option C is 74%. So, 74% corresponds to a face-centered cubic or a cubic close packing structure. So, the correct option is option C, that is 74%. Now, we will move on to the fourth question. In naturally occurring corundum, the oxide ions form the hexagonal close packing and aluminium ions occupy 2/3 of the octahedral voids. What is the formula of the corundum? Corundum is the oxide of aluminium. Okay. So, let the number of oxide ions be equal to N. Let the number of oxide ions is equal to N. It is given that oxide ions form a hexagonal close packing. So, they form a HCP arrangement or hexagonal close packing. So, the number of octahedral voids in a hexagonal close packing will be equal to the number of oxide ions present. We have given the number of oxide ions as N. So, what will be the number of octahedral voids? The number of octahedral voids will also be equal to N. Okay. Now, it is given that the aluminium ions occupy 2/3 of the octahedral voids. So, what will be the number of aluminium ions? Number of aluminium ions will be equal to 2/3. So, 2/3 of octahedral voids. So, that will be 2/3 N, where N is the number of octahedral voids. Okay. So, we have the number of aluminium ions as 2/3 N and the number of oxide ions as N. So, what will be the ratio of aluminium versus oxygen? So, that will be equal to 2/3 N is to N. So, that is 2/3 is to 1, or that is equal to 2 is to 3. So, what will be the formula of the oxide of aluminium, that is corundum? It will be Al2O3. Okay. So, here it is given the oxide ions form a hexagonal close packing. The aluminium ions occupy 2/3 of the octahedral voids, and we have to find out the formula of the corundum. If the oxide ions is N, the number of oxide ions is N, and if it forms a HCP arrangement, we can see that the number of octahedral voids will be equal to the number of oxide ions. So, both will be equal to N, and it is given that 2/3 of the octahedral voids are occupied by the aluminium ions. So, the number of aluminium ions will be equal to 2/3 N. So, the ratio will be 2/3 is to 1. So, the formula will be Al2O3. Now, we will move on to the fifth question. A compound is formed by two elements X and Y. Atoms of the element Y as anions make CCP, that is cubic close packing, and those of the element X as cations occupy all the octahedral voids and half of the tetrahedral voids. What is the formula of the compound? Okay. So, in this question, we can see that the atom X occupy both octahedral and tetrahedral voids, and we have to find out the formula. So, let us see how it is done. We have two elements X and Y. The atoms of the element Y are the anions, and Y make a CCP arrangement. Now, let the number of Y atoms is equal to 2n. And if Y make a CCP arrangement, then the number of octahedral voids in CCP will be equal to the number of atoms of Y. So, that will be equal to n. Okay. Now, what will be the number of tetrahedral voids in CCP? We know that the number of tetrahedral voids in a closed packed structure will be equal to twice the number of atoms surrounding it. So, 2 into number of Y atoms present, so that is equal to 2n. Okay. So, we have considered the number of Y atoms as n, and if Y forms a cubic closed packed structure, the number of octahedral voids will be equal to the number of atoms of Y, which is equal to n. Now, the number of tetrahedral voids in any closed packed structure will be equal to twice the number of Y atoms present, and that is equal to 2n. Now, we have to find out the number of X atoms. It is given that the X atoms occupy all the octahedral voids and half of the tetrahedral voids. So, what will be the number of X atoms? Number of X atoms will be equal to, if n is the number of octahedral voids and if X occupy all the octahedral voids, then number of X atoms will be n plus X atoms are also occupying half of the tetrahedral voids, and 2n is the number of tetrahedral voids. So, 2n into 1 by 2. So, that is n plus n, which is equal to 2n. Okay. So, the number of X atoms is 2n and the number of Y atoms is n. So, what will be the formula of the compound? It will be X to Y. We can take the ratio of X's to Y will be equal to 2n is to n. So, that is equal to 2 is to 1. So, the formula, corresponding formula will be X to Y. Okay. So, in this question, the X atoms are occupying both octahedral and tetrahedral voids. So, you have to find out the number of octahedral voids as well as the number of tetrahedral voids. So, from that you can calculate the number of X atoms and the formula of the compound. Now, we will move on to today's session, and today's topic is the use of crystals as diffraction grating for X-rays. We have seen that while discussing about the nature of a crystalline solid, crystals can act as a natural three-dimensional diffraction gratings for X-rays because their atomic planes are spaced at distances comparable to X-ray wavelengths. We know that X-rays are electromagnetic radiations of very short wavelength. Usually their wavelength is of the order of 10 to the power of minus 10 meters or of the order of angstroms. We know that 1 angstrom is equal to 10 to the power of minus 10 meters. Okay. So, crystals, they are natural three-dimensional diffraction gratings for X-rays because their atomic planes have a spacing or distances comparable to the wavelength of the X-rays. So, when X-rays strike a crystal, they are diffracted or scattered by the atoms, and this diffraction produces a characteristic pattern or a unique diffraction pattern. Such a phenomenon was first demonstrated by Max von Leu in 1912 and further confirmed in the same year by Walter Friedrich and Paul Knipping. They were able to photograph specific diffraction patterns that was observed during their studies on zinc blende and copper sulfate crystals using broad band X-rays. So, the crystals can be used as diffraction gratings for X-rays was first experimentally demonstrated by Max von Leu and further confirmed by Friedrich and Knipping, and they were able to photograph specific diffraction patterns during their study. Now, the question arises, why crystals can be used as diffraction gratings for X-rays? The first point is that because of their periodic structure. We have seen that crystals or crystalline solids have a regular repeating 3D arrangement of atoms, creating planes of atoms with consistent spacing. We know that the atoms are placed at specific points called the lattice points, and they are arranged in a periodical array of points or in a specific geometrical pattern. There will be an infinite number of parallel planes one over the other, and the spacing between these planes will also be regular. So, because of such a periodical structure, a regular repeating three-dimensional arrangement, they can create different planes of atoms with consistent spacing. Now, the next is about the interatomic spacing and wavelength. And because of these consistent spacing between various planes in a crystal, the distance between these atomic planes is on the same order of magnitude as the wavelength of X-rays, as we saw in the previous slide. That is, the X-rays generally have a very short wavelength, and it is usually of the order of 1 angstrom. So, the spacing between these planes is also of the order of 1 angstrom. So, this match in the wavelength of the X-rays as well as the interatomic spacing is crucial for the interaction to produce diffraction. So, when X-rays strike the crystal, they are scattered by the atoms. Now, because of this ordered structure, these scattered X-rays interfere constructively in specific directions and destructively in some other directions, creating the observed diffraction pattern. Now, what is meant by constructively and destructively? Constructively means it will reinforce. In phase, the waves will be in phase, which is also called constructive interference. And destructive means they will be out of phase. So, that is destructive interference. So, when X-rays falls on a crystal surface, the atoms in the planes, in different planes will get scattered, or they scatter the light, and because of the ordered structure, these scattered X-rays interfere either in constructive way or in destructive way, creating a unique diffraction patterns. Now, we have seen that crystals are used as diffraction gratings for X-rays. So, what about other samples and other electromagnetic radiations? If we consider amorphous solids or amorphous materials, we know that such materials do not have a regular periodic arrangement like most liquids, gases or other amorphous solids. So, they do not produce a useful diffraction pattern because there won't be any regular planes for the X-rays to interact with in a predictable way. Now, what about visible light instead of X-rays? If we consider visible light, they has a much longer wavelength than X-rays, meaning its wavelength is too large to see or diffract from individual atoms and their spacings within the crystal. So, when we pass visible light, they just simply pass through or average out the atomic structure, providing no detailed information. So, amorphous solids cannot be used because they do not have any regular periodic arrangement. And when we consider visible light, their wavelength is too large to diffract, to see or diffract from the individual atoms. So, we cannot see specific or characteristic diffraction patterns as observed with diffraction for X-rays. The fact that crystals can be used as diffraction grating for X-rays led Sir William Henry Bragg and his son Sir William Lawrence Bragg develop a powerful method for studying the internal structure of crystals using monochromatic X-rays. Okay. And the father and the son were jointly awarded the Nobel Prize in Physics in 1915 for their detailed study on X-ray using X-ray diffraction. So, W.H. Bragg and W.L. Bragg, based on this X-ray diffraction, derived an equation or law known as the Bragg equation or Bragg's law. So, let us see what is Bragg's equation or Bragg's law. The law states that when the X-ray is incident onto a crystal surface, its angle of incidence theta, that is the angle at which the X-ray falls on the crystal, it is the angle of incidence theta, that will reflect back with the same angle of scattering theta. Okay. So, the law, Bragg's law, the fundamental principle is that when X-ray is incident onto a crystal surface, its angle of incidence, let us say theta, which is also called the glancing angle. Okay. So, angle of incidence are also called glancing angle. So, that will reflect back with the same angle of scattering theta. Further, for a strong reflection or diffraction to occur, that is of maximum intensity, the path difference between the X-rays reflecting from adjacent planes must be an integer multiple of their wavelength. Okay, the path difference between the X-rays reflecting from successive planes must be an integer multiple of their wavelength, resulting in a constructive interference. As I said earlier, constructive interference means the waves will be in phase contributing to maximum intensity. Okay. So, Bragg's equation or Bragg's law mainly depend on these 2 points, that is the X-ray is incident onto a crystal surface, when X-ray is incident onto a crystal surface, its angle of incidence theta will reflect back with the same angle of scattering theta, and for a strong reflection or diffraction to occur, the path difference between the X-rays must be an integer multiple of their wavelength lambda, resulting in a constructive interference. So, this is the Bragg's equation or Bragg's law represented as n lambda is equal to 2d sin theta, where lambda is the wavelength of the X-rays, d is the spacing of the crystal layers or the path difference, theta is the incident angle, that is the angle between the incident ray and the scatter plane, and n is an integer ranging from 1, 2, 3, etc. It is also called the order of diffraction. Okay. If n is equal to 1, we may call it a first order diffraction. If n equal to 2, it is a second order diffraction. If n equals 3, it is a third order diffraction, and so on. Okay. So, n lambda equals 2d sin theta is the basic equation representing the Bragg's law, or we may call it as Bragg's equation, where lambda is the wavelength of the X-rays used, d is the spacing between the crystal planes, theta is the incident angle or the glancing angle, n is an integer where n equals 1, 2, 3, etc., which is also called the order of diffraction. Now, let us see how to derive the Bragg's equation. Bragg considered the X-ray diffraction by crystals in terms of the reflection of X-rays from the successive parallel planes of motifs in them. Motifs means structural units in them. For example, as you can see in the figure, you can see different layers of planes represented as A, A dash, B, B dash, C, C dash. So, on each layer you can see the motifs or the structural units represented. Okay. And let the spacing between the two adjacent layers, for example, A dash and B dash spacing. So, let the spacing equal to D, or the interplanar spacing is equal to D. Okay. Now, we can see that the X-rays fall on these crystal planes. Now, let us see what happens. Let PQR and LMN represent the paths of two parallel rays reflected respectively from the planes A dash and B dash. So, this is PQR and this is LMN. PQR onto the plane A dash and LMN onto the plane B dash. If we measure this distance, that is QM, that is nothing but the spacing between the two planes, and QM is equal to D. If we draw two perpendiculars, namely QS and QT, these are the perpendiculars drawn to LM and MN respectively. Okay. So, if we consider two triangles SQM and TQM, these two triangles, we can see that these two triangles are congruent triangles. So, what is meant by congruent triangles? Congruent triangles means they have equal size, shape, and the corresponding angles will also be equal. So, they are called congruent triangles. Okay. Now, when the X-rays falls on the crystal surface, we can see that the incident angle is equal to theta, and that theta is marked here. Okay, the incident angle is theta. Now, from the figure, we can find that SM is equal to QM sin theta. SM equals QM sin theta from simple geometrical considerations. So, that is equal to QM is D, so that is equal to D sin theta. Similarly, if we take the other side, that is TM, so TM will also be equal to QM sin theta, so that is also equal to D sin theta. Okay. So, what will be the path difference between the rays? The path difference between the rays will be equal to SM plus TM. So, that will be equal to D sin theta plus D sin theta. So, that is equal to 2D sin theta. So, we have find out the path difference between the rays from simple geometrical considerations. So, it is SM plus TM, which is equal to 2D sin theta. Now, the reflected rays will be in phase, that is, they will be of maximum intensity only if the path difference is equal to an integral multiple of the wavelength lambda. The path difference, if the path difference is equal to an integral multiple of the wavelength lambda, then the reflected rays will be of maximum intensity. Or we may say that the condition for constructive interference or the condition for the reflections of maximum intensity, the path difference should be equal to n lambda, where n is an integer called the order of diffraction or integer multiple. So, n lambda. So, we can see that n lambda, the path difference, will be equal to, in the previous slide, we saw that the path difference between the rays, from the figure you got it as 2d sin theta. So, here we can write n lambda is equal to 2d sin theta. So, this is what is called the Bragg's equation or Bragg's law. Here lambda is the wavelength of the X-rays used, n is the order of the diffraction. The value of n can be equal to 1, 2, 3 and it is called the order of diffraction. And what is d? D is the spacing between the adjacent planes and theta is the incident angle. So, this is how we derive the Bragg's equation, that is n lambda is equal to 2d sin theta. So, the basic condition is that the path difference should be an integral multiple of the wavelength lambda. Then only we will have reflections of maximum intensity, or we may call it as for constructive interference. Okay, so n lambda is equal to 2d sin theta. Now, let us see what is the significance of the Bragg's equation. The main significance of Bragg's law or Bragg's equation lies in deciphering the crystal structure. So, by measuring the angles theta at which constructive interference occurs, so we can calculate the spacing d between the crystal's atomic planes. So, the resulting pattern of spacing provides a fingerprint that reveals the material's unique crystal structure. The diffraction pattern produced by each crystalline solid is completely unique, thereby serving as a fingerprint that reveals its characteristic properties. So, this is the significance of the Bragg's equation. And also using this equation, that is, we have n lambda is equal to 2d sin theta. So, from this you can also calculate the spacing, right. So, d is equal to n lambda by 2 sin theta. So, if we know these parameters, you can calculate the spacing between the lattice planes using the same equation. Okay. And also you can calculate the edge length by the equation dHKL is equal to A by root of h square plus k square plus L square. So, once you get the d value using the Bragg's equation, you can use that value for finding out the edge length of the unit cell in various structures using this equation dHKL is equal to AHKL by root of h square plus k square plus L square. So, today we have discussed about the use of crystals as diffraction gratings for X-rays. So, crystals can act as diffraction grating with an ordered atomic or molecular structure in a crystal lattice. The spacing between these atomic centers in the crystal lattice is comparable to the wavelength of the X-rays, and we have seen that it is of the order of 10 to the power of minus 10 meters, that is of the order of angstroms. And when a beam of these waves strikes on a crystal, it interacts with these regularly spaced lattice planes or regularly spaced atoms. So, this interaction causes the waves to scatter, interfere, thereby creating a distinct diffraction pattern. And we have seen the Bragg's law, which is n lambda is equal to 2d sin theta, and We also saw how to derive the Bragg's equation. Bragg's law is the cornerstone of X-ray crystallography and other diffraction techniques, providing a mathematical basis for how crystals scatter X-rays. So, in the next class, we will discuss a few problems based on Bragg's equation. Thank you.